Hi everyone, so this is Unit 8. We're going to be studying kinetics, thermodynamics, and equilibrium. So when we refer to kinetics, we'll be talking about reaction rate, collision theory, reaction mechanism, and the factors that affect the rate of the reactions. We'll also be looking at thermodynamics. Thermo means heat energy. Okay, dynamics means motion. So we'll be looking at potential energy diagrams, heat of reactions, endothermic and exothermic reactions we kind of already know about, but we will be revisiting those. And we'll be learning about the additional terms here: activated complex, activation energy, effective catalyst on a reaction, and stability. So we will be looking at an additional table on our reference tables, and then finally equilibrium, which is when rates of a reaction are equal to each other, and we'll be looking at those later on in the unit. So let's start with lesson 1, and our objectives for this lesson will be to define kinetics, reaction mechanism, rate determining step, activated complex, catalyst, inhibitor, and the collision theory. You will also state the collision theory and determine the 6 factors that affect the rate of a reaction. So let's start. Kinetics, what is it? It is the study of the rate or speed at which a reaction will occur. A reaction is the breaking and reforming of bonds to make entirely new compounds as products. The reaction mechanism, or pathway we should say, okay, so a mechanism would be a pathway, kind of like a road. Reaction mechanism is a step-by-step process needed to make a product. So how you get from point A to point B, like a recipe or like on a roadmap, okay? Reactants will form products. So just like when we bake a cake, we must follow directions. You can't omit any steps, you can't change the order of these steps, and you cannot omit any reactants or ingredients if we're talking about baking. Okay, if you did any of these, then we would not get the desired products. So what I want you to do is determine whether each of the following chemical reactions is an example of a slow or fast reaction. Explain why knowing the relative rate of the reaction is significant. You're going to do this on your own, and we will talk about this in class, so I will check your notes. Okay, so what determines the rate of a reaction? Well, 1, the number of steps. The more steps you have mean a slower reaction, or could mean a slower reaction. So thinking about this, how many turns do you have to make on your way to Albany? Okay, if there are more turns, then it might take longer to get there. Rate determining step. This is the step that is the slowest step of the reaction, and it is the most important factor influencing the rate of the reaction. So here is a imaginary reaction here, A plus B plus C, and the rate determining step will be the slowest step, which would be right here. Okay, so here there are 2 steps in this reaction mechanism, and when we go, here's the intermediate, which is the slow step. We start off with A plus B to form AB, and then AB will be reacting with C to then finally produce our final product here, A, B, and C. Notice how the reaction pathway shows you the higher the peak, the slower it's going to be. That will determine basically the rate of the reaction. So here's an example for a reaction between hydrogen and iodine gases, okay, H2 and I2, to form 2 moles of hydrogen iodide. The first step, we take H2, and what happens is the bonds between the hydrogens will break by absorbing energy to form 2 moles of hydrogen by itself. Okay, the second step then, we would take the I2, and the I2 would then break apart by absorbing energy and form 2 iodines separately. Now what's going to happen is, finally, what we want to get this final product, H would rather bond with iodine, okay, than with itself. So what's going to happen is a new bond will be formed between the hydrogen and the iodine to form 2 moles of the hydrogen iodide, which is a new product. A new bond is formed, which now releases energy. So you have to absorb energy as you're going, and then finally energy will be released when a new product is formed. So the net reaction shows H2 plus I2 then forms 2 hydrogen iodides. Of course, these are the intermediate steps, okay? It doesn't just go from here to here and then you get that. Something is happening in between. So your 2 hydrogens and your 2 iodines are formed in steps 1 and 2, and they're used up in step 3. So the 2 hydrogens and the 2 iodines are called the intermediates, also known as the activated complex. Please put this in your notes. So if you need to go back, rewind, this is a prime example of writing out a reaction mechanism with the intermediate steps. Okay, so going on, the collision theory. Well, we have to talk about the collision theory in order to give us an idea of how a reaction is going to occur, whether a reaction is going to occur. So the collision theory, this goes back to Unit 6, relates to the kinetic molecular theory. We're talking about kinetics. So in order for a reaction to occur, reactant particles must collide. Hence the term collision theory. And they must have to do the following in order to have a reaction: the proper amount of energy and the proper alignment or orientation or direction. All of these terms mean the same thing, okay? The way they're arranged. So, for example, here's A. We have a proper alignment here, enough energy, but they don't collide. They just bounce off of each other. So there would be no reaction here. But for B, we have a collision, and now we have new products formed. Enough energy here and enough alignment to create our new product. So here is our reaction. So only when particles collide with these 2 conditions are met will there be an effective collision, which results in a reaction. Okay. Now in your notes there is a link which I will show you guys in class, but I'd like you to check that out if you can. And again, I'll show you the animation in class. So factors affecting the rate of reaction, the 6 factors that affect the rate of reaction. There is a link in your notes, and we will visit that in class. So why is it that certain reactions go faster than others? This can be explained by 6 factors that affect the rate of the reaction by changing the number of effective collisions. The more effective collisions, the faster the reaction. Okay, so please put that in your notes. It is not in your note packet. So the more effective the collisions, or the more effective collisions we have, the faster the reaction is going to be. So let's look at factor 1, nature of reactants. Ionic substances react faster. You have to know this. Okay, ionic is smaller, so we have less bonds to break, less steps. Here are some examples: sodium chloride, aqueous solution, silver nitrate. Double replacement reaction, sodium nitrate and now silver chloride, and the ions break up into solution, okay, positive, negative ions in the solution, and we end up with an AgCl as a solid, okay, not soluble. Only one step, if you notice. Okay, there's only one step occurring here. Now, covalent substances obviously will react slower. Okay, so it's the opposite. Covalent have larger molecules, so there are more bonds to break, so there are more steps. And let's look at an example here. We have methane gas and oxygen gas to form carbon dioxide and 2 water molecules. This is combustion, okay, just to remind you guys. Combustion. Sorry about that. What we need to do is we need to break the 4 CH bonds and the 1 O2 bond to form 2 carbon dioxide bonds and 4 OH bonds, okay, between the H2O. So there's a total of 4. So in order to do that, you have several more steps to work. All right, so number 2, okay, the factor number 2, which is not a 3 in your notes, but this should be a 2. concentration, just like we learned in the last unit. The increase in concentration will increase the reaction rate. Okay, kind of doesn't make sense, but more molecules in the upper layer here have a chance of combining, so you're going to have more effective collisions. That's the whole point. You have more stuff in your solution, so there's going to be more effective collisions. So let's look at the diagram here. Low concentration, meaning less solute in the solvent, fewer collisions. The higher the concentration, the more solute you have, so then the more collisions you're going to have. Therefore, you're going to have an increase in reaction rate. The more particles in a given space, the less space between the particles, and you have more collisions. It's all about the collisions, guys. So pressure would be factor 3. Increase in pressure will increase the reaction rate. And it affects gases only. I have to stress this, okay? Gases only. Increasing pressure decreases the volume. Decreases the volume, which decreases the space between the particles. And therefore you have more collisions. Thinking about being packed in a very tiny room, okay? More people in a room, you're hitting each other more, you're bumping into each other, you have no space. Factor 4, temperature. Increase in temperature will increase the reaction rate. What happens here is you have greater speed, which causes more total collisions. So think about this. You'll have more collisions going 70 miles an hour than you would going 30 miles an hour, or more effective collisions, we should say, more damage. The greater the average kinetic energy, remember that's temperature, collisions will take place. Okay, so greater speed will mean more collisions, and greater average kinetic energy or temperature collisions take place with more energy. Finally, two last factors here. Factor 5, surface area. So if we increase the surface area by making pieces smaller, then the reaction rate will increase. It increases the reaction rate. So increasing surface area exposes more reactant particles to possible collisions. And that's what's happening. Remember, all about the collision theory here. So if we have one block and we break it up into several other pieces, all of these surfaces will be exposed to more collisions and therefore a greater reaction rate. Okay, so how many surfaces are there? That's what you need to ask yourself. Sorry about the bell, guys. And finally, our last factor affecting reaction rate is a catalyst or an inhibitor, and this you will have to add to your notes. Catalyst will speed up the reaction without changing the nature of the reactants or the products. So it doesn't change what you end up with at the end. It doesn't change anything with the reactants. It just provides a shortcut or an alternative pathway. And it lowers the activation energy for the reaction. So this is the amount of energy needed to get the reaction to go. So if you're lowering the activation energy, it's just going to speed it up. Okay, less energy, it gets to that activation point much sooner. Now an inhibitor is the opposite. So an inhibitor will actually slow down a reaction by adding additional steps, kind of like a roadblock or a detour. And what happens here is that the activation energy is going to increase, which then takes it longer to get to that activation point for the reaction to go forward. So it's going to slow it down or inhibit the reaction. Okay, so that ends our lesson 1. And then what I want you to do is be prepared to answer questions related to the lesson in class, and make sure you've determined the rates of the reactions that are on page 2 of your notes. Thanks, guys.